All right, students, so here's a review for trigonometry. I'll try and keep it under 10 minutes, but I'm not sure I can. I'll do my best. So we started with right triangle trigonometry, and what did we learn? We learned, all right, if this is our reference angle here, so we were standing here at this angle, the longest side, so the one that the right angle is pointing to, is always our hypotenuse. And then the other side that's connected to us is our adjacent side. And then whatever we're looking at, the side we're looking at opposite us, the one not connected to us, is our opposite side. And so those are our three trig functions: sine, cosine, and tangent. And we abbreviate those so they fit on our calculator as sine, cosine, and tangent. So sin, cos, tan. And what do they represent? They just represent ratios of side lengths. They're just these functions that tell us, okay, so the sine of this angle is the length of the opposite side over the length of the hypotenuse. And the cosine is the length of the adjacent side over the length of the hypotenuse. And the tangent is the length of the opposite side over the length of the adjacent side. So let's look at another example. So these are our trig functions. These are our inverse functions, which we'll talk about in a second. So how trigonometry works is basically because the angle is dependent on the side lengths, right? And vice versa. So if we have a triangle, if this angle, say, gets bigger, then the length of this side opposite it has to be longer, right? So as this angle grows, so does this side length. And then by nature, also, like, this side length would also have to grow. So the angles are dependent on the sides and vice versa. So that's how trigonometry actually works. So if we know the sides, for example, we know an angle of, say, 30 degrees, and we looked at special triangles. So if I know that this angle is 30 degrees, I know that the length of this opposite side here is going to be 1/2. And we actually looked at specific cases. So like a 30, 60, 90 triangle, the sine of this angle is always 1/2. And take a look. The length of this side is 0.5. The length of this side is, the hypotenuse is 1. So the length of this side is 1/2 of the hypotenuse. And then we learned that the cosine of 30 degrees was radical 3/2. So radical 3 is about 1.7. So if I divide 1.7 by 2, that's about 0.85 something. So that's the length of this side is about 0.85. And this is 1. So that's the ratio is radical 3/2. So if we think back to our dilations, that will help us explain these things. Oh, we also learned about 45, 45, 90 triangles, which are right isosceles triangles. Those are super easy for us to solve because they have two congruent legs. So if we know one of the legs, we know the other one. We looked at dilations earlier, right, in our similarity unit. So if we think about a 30, 60, 90 triangle, or any triangles for that matter, if I just dilate it, right, so this angle is still 30 degrees. So with similar triangles, we remember that the angles stay the same, and then the side lengths increased by some scale factor. So if this is still the sine of 30 degrees, the opposite side over the hypotenuse is still going to be 1/2. So all that's saying is this opposite side is always going to be half the length of the hypotenuse. And so if we measured these, you would see that this is actually, in fact, 1/2. So that's all that represents. All of these trig functions are just ratios of side lengths. And because triangles are similar, that 30-degree angle is always going to represent 1/2. For if we have a 30-degree angle in a right triangle, the opposite side is going to be 1/2. So then we expanded our knowledge of right triangle trigonometry to look at other triangles. So if we have, say, this triangle here, which is just a scalene triangle with all acute angles, and remember our notation in trigonometry, so if we have angle D, angle E, angle F, so these vertices, right, we label the vertices, these points or angles, with capital letters. The side opposite, we label the length of this side with the lowercase d. So this is capital F, lowercase f, capital E, lowercase e. And the reason for that is it makes it really easy for us to spot opposite sides. So even though the triangle is not a right triangle, we can create right triangles by going ahead and dropping an altitude. So if I just drop this height or altitude, they're synonyms, they mean the same. the height of this triangle is formed by this perpendicular line going to the vertex. And we learned how to do that. We can just do it with a ruler. We could construct it too if we needed to, with a compass. So you could think about how to do that. So this is our height. So the sine of this angle D is the opposite side over the hypotenuse. And this side F is the hypotenuse of this triangle right here on the left. So we can write that down. Sine of angle D equals this H over F. So the height of this triangle over F. Well, I can rewrite this if I want to get rid of the fraction. I want to get the height by itself. I can multiply both sides by F, and I get the height of the triangle equals the length of this side times the sine of this angle. Now, this is very helpful because if I know the height of the triangle, I can figure out the triangle's area, right? Because area is just 1/2 base times height. This side E is the base, this is the height, so 1/2 of E times H is the area of the triangle. But look, I know what H equals. H equals F times the sine of D. So if I know the length of F and I know this angle, it's that side angle side relationship, then I know the area of the triangle. And that would be the area formula for this triangle. So that's our side angle side area, 1/2 E times F times the sine of D. And the reason that works is because the sine of angle D equals the opposite side over the hypotenuse. So we're just using trigonometry to find the height of the triangle. Then we expanded this to actually help us find other things in the triangle. Because we know, say, the sine of this angle over here also equals this height, which is the same height of the triangle, over this hypotenuse, so the hypotenuse of this triangle on the right here. So we can rewrite that. So the height also equals the length of side D times the sine of this angle. Well, if these two things equal H, I can set them equal to each other. That's the transitive property. So if I set them equal to each other, and I reform these expressions, and I get all of the F's on one side and all the D's on the other, then this gives us the law of sines. So the length of side D over the sine of angle D equals the length of side E over the sine of this entire angle here, E, equals the length of side F over the sine of this angle F here. And that's just that crisscross applesauce relationship where we see, all right, well, the length of this side over the sine of this angle equals the length of this side over the sine of this angle, which equals the length of this side over the sine of this angle. So that's really helpful for any triangle, not necessarily a right triangle. If we know, say, two angles and a side, then we can figure out all the other missing pieces. We also looked at law of cosines and how we could figure out those sorts of things, missing other parts of triangles with law of cosines, but we didn't get into too much detail with that. The last thing we really looked at was triangle area on the coordinate plane, and we figured out a lot of different ways to solve these. We could use that side angle side relationship if we knew one of the angles. We also used distance formula to figure out, say, like the length of this side and the length of this side, and then it's 1/2 base times height. But we also saw that really cool way where if we just make this into a rectangle and then find the areas of these other right triangles that are very easy because we can just count the length of the height and the length of the base, the length of the height, the length of the base, length of the height, length of the base. It's just 1/2 base times height. Then you can just do some subtraction to figure out the area of this triangle here. So here's an example of that, like for this one down below. If I know the area of this rectangle is 11 times 12, and I know the area of this triangle number 1 here is 1/2 3 times 11, and I know this triangle is 1/2 4 times 7, and then I know this one, it's not 4, sorry, 9 times 7, and I know this one here is 1/2 12 times 4, and then I can just subtract those. I get the area 60. So I hope this helps. Please let me know if you have any questions, and I'll see you in class.